at the end, we took a little tour of the solar system, which I want to finish up today. And what's really interesting about that is that we're left with a story of how this place came to be. And we get a basic layout for, where things are. And the story that we tell is very conservative, and it very much leans towards saying that the solar system is essentially more or less as it was when it formed, and we can tell the stories of the different objects in it by their location with respect to the formation. And this week, I'm going to continue that story a bit. And I want to go through a little bit of the history of how people started with that idea, how they tried on a bunch of other ideas, and then they kind of returned to the original idea, which is a really strange thing that you don't see it happen a lot in science. They spent 100 years trying on different ideas, and now we're essentially, 300 years actually, now we're essentially back to the maybe a slightly more evidence-driven version of the theory that we had in the 1700s, but it's essentially the same idea, which is called the nebular hypothesis. So we're going to talk about that story a little bit. Then we're going to get into the crust, tectonics, different types of tectonic theories. You all are very well aware of plate tectonics, which is really only been popular for the last 50 or 70 years, which is kind of shocking. So there was essentially a competing idea with that originally, which was something like the Earth used to be smaller, and we'll talk about that. And then finally, I want to talk about the core and magnetism, because like I said, magnets are one of the most poorly understood phenomena in the universe. And so we're going to try to make sense of that. I hope that everybody can walk out of here explaining how a magnet works without using math or anything abstract. All right, so that's a lot to get through. So let's dive right in. Oh, I also brought a little gadget today. I'm going to show you a little, I made a little electric motor, and this will be kind of fun. I'm going to get to try out the projector. Cool. So the basic way that we look about that we check out the origins of the solar system is we think about what's similar amongst the planets. They all lie in the same plane. They all rotate, or they all orbit in the same direction. And so those basic similarities are what drew folks into this idea that there was some sort of cloud of dust that was acting magnetically and electrically and gravitationally upon itself, and it collapsed, right? And this was Laplace's theory in the first place. There were some other contributors to it in that same century. Laplace formalized it. And what's really interesting about this theory is that it leaves us with this gaping crisis, which is, if this is how the solar system formed, why is the sun not spinning like crazy right now, right? And this is a huge problem right up to today. And so the stories that we explore about the origins of the solar system all come down to trying to resolve that problem. Because remember your figure skater, when he brings his arms in like this, he spins faster, right? This is conservation of angular momentum. And angular momentum turns out to be everything. It's going to come into how our own magnetic field is generated in terms of the core dynamics and mantle dynamics. And so we will never get enough of the conservation of angular momentum, and it is the absolute monster in the room when it comes to explaining the solar system. What else can I say about this standard idea? So there's something really, I wanted to make a slight aside here and revisit the concept of these stories a little bit. And I want you to really think about what science is trying to accomplish in the Western world, which is different from what other forms of narrative presentation are trying to accomplish. And what's really interesting is that in a lot of other cultures, there's not really a separation of the mechanistic stories that science tells from the meaning-rich stories that are told about how the human dynamics play out. They kind of get wrapped into one. In our world, we separated these out. We tried to separate them out by saying that science has nothing to do with religion, which is often a doctrine of meaning, of morality. Art is weird, though, because art in our modern society almost fills a lot of the role of religion because it allows us to seek meaning through people's expression and our own interaction with it and interpretation. And the real question you have to ask yourself is, are science and art fundamentally different? Is science an art, right? Is it a particular form of storytelling that actually is expressive and tells us something about how us humans look at our world? I think this is the case, and it seems like I think there's a lot of wisdom coming from the native astronomers about this. I'm going to read you just a little piece of this. Again, this is coming from Cajete, who's this Navajo scientist. He writes, "The word science has only recently been used to depict systems of knowledge that refer to the multidimensional world of nature and the people's ways or traditions of relationship with the world. Use of science by native peoples contains this type of understanding. This use to describe the experience and traditions of native peoples remains controversial given the biases and scientism of Western scientists." Does anybody know what that word scientism means? You guys heard that? It's like a politically hot word right now, but I think it's worth talking about. Anybody? Ever heard that word before? Wow. All right, well, yeah, so that's a good one. Scientism refers to a belief structure in a particular scientific theory. You know, perhaps you guys spent the last few years in this pandemic mess, which was highly politicized, unfortunately. And one of the tagline phrases was "trust the science," right? And this is a devastating concept, actually, because science, as we've hopefully learned so far in this course, is constantly on the move, right? We're always learning something new. And so if you understand that and you say, okay, I'm going to trust the scientific process, I'm going to trust that we're going to come up with the best understanding tomorrow, because that's how it works, right? It's got to be this progressive entity. Now, if you confuse the concept of trusting the process with trusting the theory, then you end up in the realm of scientism, and that's what this author is talking about. Scientism is the idea that you have faith, almost a religious faith, in a particular theory, right? And so this has been a real salient criticism of Western science in the past few years, and I think that this book was written before the pandemic. So this has obviously been a concept that's been in operation for a while, but we have to be careful not to ever fall in love with our own ideas. And this becomes really difficult when you're fighting for Nobel Prizes and funding and everything else, and you build a career on the back of some theory. It's very, very difficult from a human perspective, integrated into that Western civilization where your career is tied inherently to your theory. It's very difficult to change your mind when you're 40 years into a career about that. And so this is a real problem that your generation could stand to iron out, because the incentive structures that are tied to science inherently reinforce the old. And to some extent, that's good that it's conservative, right? We want it to be difficult to change people's minds about science. It needs to be a really compelling theory, right? But it can get out of control to the point that we can't move forward either. Or that we move forward with some mistaken idea because some brilliant person came up with the concept that we have, and they've done so much brilliant work that we can't imagine they could have been mistaken about any particular aspect of it. Okay, I'm going to finish this. Herbert Reed, pioneer arts educator, wrote, quote, "Science is the explanation, and art is the expression of the same reality. That definition has important ramifications for native science. Within indigenous consciousness, science is also an art form. which incorporates both an objective explanation for how things happen in the natural world and a way of looking at how those things happen. The idea that science and art are two sides of the same coin is what indigenous people have always tried to convey, and this is also in the margin of Western philosophical thinking, as philosophers, artists, humanists, and religious leaders insist that science is a part of the greater whole of human expression. In Western society, conflict about the definition of science has been underway since the time of Galileo, when science was separated from religion. Religion became the antithesis of science, although some would describe science as a kind of religion. These controversies continue to characterize Western philosophical traditions. Okay, so he's more or less saying what I'm saying, and we have to be really, really careful at all times that we don't convert science back into a religion, that we understand that it has an interpretive element, an expressive element, which comes from our own experience in the world. We see everything as being a reflection of our lives, and this becomes particularly important when we get into cosmology next semester, because the entire concept of the birth of a universe reflects our own experience having a birth as individuals. We all are born and we will all die. And so this has been a fundamental lens through which we view the entire cosmos. Of course, the cosmos must have a birth and a death because that's the way it works for us. And we're going to unpack that a bit more next semester. But as we go through some of these stories, I want you to really think about how those ideas may have reflected the spirit of the times and why we're at where we're at today, because quite frankly, we haven't really solved this fundamental crisis with the angular momentum in the solar system. And I think that our theories of the origin of the solar system will continue to evolve. Maybe one of you will evolve it, actually. There's certainly huge gaping holes that need to be solved. And whether that ends up looking something like the nebular hypothesis, or whether it looks something more like one of these other theories, or something altogether different. So let's talk about some different theories. All right, so one of the theories for what could happen in one of our modern explanations for what happens to all of this angular momentum is that there's these little jets that are exuded from young stars, where they're basically squirting out material. And you can see this in the upper left-hand corner here, which is supposed to be a star-forming region. You see these little jets coming out of the side. This is one idea for how you can kick off a lot of spin energy, essentially, and leave your star still. There's some problems with this because obviously the planets are rotating furiously. They have a tremendous amount of angular momentum. And actually, in our solar system, Jupiter has most of it. So people started thinking about some other ideas. Going all the way back, this is actually Descartes' drawing of the solar system. And Descartes this was in 1629. And Descartes viewed that the whole universe could be described by these rotating vortices of ether, essentially. And this, we talked a bit about the medium which transmits light and gravity. And today we have this relativistic idea that there's a stuff called space-time. But it's strange because space-time is dynamic. That means it's moving. So then maybe there's a stuff called space. But then we run out of a word for what's in between the objects out there. And so it isn't totally different how we look at the world from how Descartes looked at it. We have these things called magnetic fields, gravitational fields, and of course fields are also dynamic. They describe something in motion. So whatever it is that the fields are measuring the activity of still remains to be elucidated, which is really fascinating. So despite the fact that we can handle these things very nicely with mathematics, and we have this concept of fields, which we're going to keep coming back to over and over again today, It's not quite clear what it is that's swirling about out there. Well, Descartes thought it was these vortices, and then Kant came along in 1755, and he looked at the nebula, like the one we had on the last slide, and he thought, okay, well, that's maybe where the stars are forming, and that's maybe where planets are forming too. So Laplace came along at the end of the 1700s and actually came up with this idea that the nebulas collapsed into a star. And if it did that, the remaining material would kind of spin out nicely, just like our figure skater's arms, into a flat disk, which would form all the planets. And really, this model was worked on all the way up into the 1900s by different people. But alongside it, there was some really interesting catastrophic ideas that occurred as well. The angular momentum problem became hot almost immediately, and nobody had any great ideas about it until the 1900s. But the 1900s were spent almost entirely trying to iron this angular momentum business out. One idea was put forth by James Jeans, I think in the early teens. And Jeans, we're going to come back to Jeans because he was instrumental in developing our understanding of the sun. And I absolutely can't wait to talk about the sun because people have had completely crazy ideas about how the sun works. And then starting in about the 50s or so, it was done. And we haven't really changed our mind about it since then, which is quite fascinating. Anyways, we'll get to the sun later. So Jeans had this idea that there was another star that came near our star and took up, interacted with it in such a way that it gravitationally took up tidally, just like the moon, it tidally removed some of the angular momentum from the equation. And this is actually a really interesting theory because almost all stars are found to be formed in pairs. Really, almost all of them. And so, a big question today is, where is our sister star? Did she wander off? Did she explode? And so, this tidal hypothesis was entertained heavily, and honestly, people are still entertaining it. There was another idea that came along that actually, and this was Raymond Littleton in the late 30s, who said, okay, well, actually, I think that star, that our sister star, actually collided with our star. And in that collision, much like our idea of how the moon formed, it took a bunch of the angular momentum out of the equation when it smashed into it. And what's really interesting about these theories is that they were never totally disproved, right? People just tended to not favor them. And in general, I would say that we tend to not favor these catastrophic explanations for how things formed. And I wonder, going back to the concept of interpretation and storytelling, if those theories are just not pleasant to look at because we really want to view the world that we live in as stable and predictable and safe, fundamentally. And if we start coming up with stories about how things formed, and you see this in geology too, we're very allergic to catastrophic explanations for geology. And there's some politics to that too. The early geologists were basically divided into two camps. One of them was hardcore fundamentalist biblical interpreters, and the other people were more skeptical of that. And it turned out that the people that were coming up with catastrophic explanations in order to shrink the timescales of things to fit the Bible, they fell into the religious fundamentalist camp. And so there's a good reason why the catastrophic explanations were also ignored. But I think there's more to it than that. I think there's really something to us wanting to impose how we think things should be upon the way that we interpret the evidence. A lot of times you hear in science, like, trust the evidence, right? And this is funny because if any of you watch true crime or anything like this, you know that the evidence is only the starting point, right? You walk into a room, there's a body, there's a gun on the floor. What happened, right? There's the evidence, and maybe you can put together some other pieces of evidence, but at the end of the day, the prosecutor has to weave a story of how that gun killed the person on the floor, and so on and so forth. So, the evidence doesn't tell the story by itself. That requires us to come and lay our ideas across it. And there's no way to separate that from what we want necessarily. As objective as we believe that we're capable of being, we're very emotional animals. There's no way around it. We really want to see things that resonate with our lives. And so I think this is happening a bit. What else? So this really brilliant gentleman who ended up winning a Nobel Prize named Hannes Alfvén brought some interesting ideas to the table. He saw everything in terms of electromagnetism, and he began to look at the sun in terms of electromagnetism. And he had this idea that actually the magnetic superstructures of the solar system as it formed would organize little pockets within the arms of the solar system that could collect and nucleate planets. And this is now being integrated very carefully into how we look at the birth of solar systems. And I've had the pleasure of sitting down with a number of people who are working kind of on the cutting edge of how star systems form. And the theory is really starting to incorporate a lot of these electromagnetic ideas. Whenever you have something that's really hot in space, when you have metallic molecules, actually these very primitive molecules or primitive atoms like hydrogen and helium, they can actually, under the right conditions, become ionized, which we talked a bit about before, and we'll talk about it more later. But essentially, they begin to take on a magnetic character, and this can organize structures. Obviously, it organizes a great deal of our outer atmosphere and protects us on Earth from cosmic rays and X-rays and things that would really mess us up, in addition to our atmosphere, and actually helps keep our atmosphere healthy. Otherwise, we end up looking like Venus or Mars, right, who doesn't even have an atmosphere hardly at all. And then what's really interesting is that a gentleman, a Soviet gentleman, let's see, came along, and he sewed up a lot of these pieces of the story into one voluminous manuscript, and essentially devised this idea of how the planets could form in this envelope that was somehow separate from the envelope in which the sun formed, and brought everybody back into the fold of the nebular hypothesis. And this has been where we're at pretty much right up until now. And, you know, I didn't mention it, but there was some other hypotheses that, okay, maybe the planets and the sun formed from totally different clouds also. This would solve the angular momentum problem. This tends to not work out because it's not clear how they would become stabilized into such a beautiful pattern so quickly. Remember, a lot of the difficulty in any one of these theories comes down to how our oldest dates only reach back to 4.5 billion years, which seems like a long time. It's not a long time, though, when it comes to building a planet or something like that. And so a lot of these theories are constrained by this idea because that's the evidence. The only evidence we have for the oldest things we can find is only 4.5 billion years old. Does it mean that everything in the solar system is only 4.5 billion years old? Absolutely not. It just means that's the oldest thing that we can reach. And a lot of this may have to do with the way that things get cooked, right? Because our dating process depends on the incorporation of these radioactive elements into freshly cooked rocks. And so, you know, maybe if we find older pieces, then more scientists will be comfortable with the idea of extending these time spans, which would allow us more time for some of these processes to unfold. You know, there was another theory that our companion star went nova. This was from Fred Hoyle, and Fred Hoyle is a really fascinating guy. He is famous for, you know, through most of the 20th century, it was entertained that much like the creationists in geology versus, one second, I'll get to you. Much like the creationists in geology versus the uniformitarians who wanted to say things happen very slowly and gradually, there was two camps in cosmology. One led by one led by, let's say, the more popular group, which was conceived of, as you know it, the Big Bang Theory, right? Which is this creation event. And then one which was led by Fred Hoyle, which was a steady state universe. And Fred tried to explain all of the different data, particularly the redshift data, which we don't have to deal with right now. And he tried to explain it in terms of the galaxies continually being renewed and pushing away from each other and so forth. The discovery of what's called the cosmic microwave background radiation pretty much kicked Fred Hoyle out of the discussion. And so we'll really get into that next semester. This is a fantastic debate, and it's far from clear what's happening, especially with all of this new James Webb data coming in. What else happened? I want to make sure I don't pass over any of these great theories. All right, we're going to have to keep moving. So another wonderful theory for planet formation, this gentleman, Marvin Herndon, who I've had the pleasure of having on the podcast too, had this idea that the sun was spitting out these giant blobs of material, and the dynamics of that are quite interesting, but essentially that they would be all coming out of the sun looking something like a gas giant, and then the gas giants would evolve. And actually, Marvin was on the cover of Discovery magazine back in the early 2000s. This was being seriously entertained, and for whatever reason, he's virtually unknown at this point, and people have retreated to the standard idea that planets form in place. Now, there's problems with planets forming in place because it's told, as it's told in your textbook, it's told that, well, it makes a lot of sense that the gas giants would form out in the far reaches because they're mostly ice and liquid and these things that require cool regions to form. However, the more we've started looking for exoplanets, we've started seeing gas giants that are actually very, very close, like Mercury close to their host star. And their atmospheres are being blasted away at a tremendous rate. And so, you know, what's really interesting is that the more popular scientists who are dealing with this are trying to explain how those gas giants could form near the sun, how they wouldn't necessarily rely on the heat distribution in order to form. And I had a really good conversation with this gentleman at Caltech named Konstantin Batygin, who is trying to rescue this idea of in situ formation of gas giants. So, and that very well may be the case, but it's interesting how we often try to patch up these paradigms instead of shifting them. Again, we don't know the answer totally, which is why there's so much debate about these things. So we'll get more to this idea in a little bit when we talk about plate tectonics, because what you see on the screen right now is essentially the alternative model for tectonics, which was entertained through most of the 20th century, which was at odds with the idea of continental drift, which is this idea that there was maybe several times there was a supercontinent. There was a supercontinent like Pangaea, you've probably heard of, which was essentially on one side of the planet, all the continents smashed together on one side of the planet, and then they've slowly been working their way apart into the configuration that we see today. And there's reasons for each one of those, but we'll give those their due time. You know, let's see, there's some issues still with the model that we have today. For instance, this nebular collapse hypothesis, even if we're able to rescue the angular momentum problem, you know, the classic way that we rescue the angular momentum problem today, in addition to these jets, is the idea that there's this cool region of dust surrounding the protoplanet, the proto-star. And the dust has the ability to frictionally rub against the star and take up the angular momentum this way, so that the star slows down, the dust begins spinning in its own little eddies, which formulate the planets. There's issues with this, though. For instance, not all of the planets rotate this way. Venus actually rotates backwards, which is really strange, right? Actually, this is a hugely difficult observation to explain. What's even worse is that a lot of the moons will rotate in different directions from one another. You can have, let's take Saturn, for instance. Some of the moons rotate this way, some of them rotate this way. And so these are thought to have been captured, but the manner by which they're captured and that they have this angular momentum in the first place is very difficult to reconcile with a homogeneous cloud that's collapsing and spinning homogeneously. So there's all these little issues that need to be ironed out, and it's not clear whether by ironing them out we're going to end up with a completely different model 5 years from now, or whether we'll somehow continue to rescue this nebular hypothesis, which everyone keeps coming back to. And there's good reason to want this nebular hypothesis to work out, because when we look out at star-forming regions, we do see these disks, and we do see disks of cold dust. And so we have to really reconcile all of these different aspects to make a theory. And this is why it's so difficult, honestly, to come up with a unified theory of anything in physics or in science, because there's so much complexity to every system. Nothing is just a perfect, ideal map of how it should be. All right, so I want to move on and talk about the Earth now. The chapter that you guys are doing in the textbook is about the Earth. You had a question. Well, there's a bunch of those we can look at. Yeah. Yeah, so then we have to, we're gonna do stars. We're gonna give them their due. And so we'll talk about those. And people have, I didn't have time to go into them, but folks have tried those on. And what's really interesting is like they seem to try on those ideas, and then it's not like anyone is saying, hey, that's impossible, right? It's just that it's not popular, right? It doesn't make it into the hearts and minds of the people that are receiving this. Whether that's like the other scientists at the Royal Academy or whatnot, it just doesn't sink in. And it's very difficult to say anything like that with great certainty. Like you said, okay, let's say we adopt a binary explanation for the formation of the solar system. How do you know it wasn't 3 of them? How do you know it wasn't 7, right? So science, the stories we tell tend to be hyper-conservative, like I said. Why do we say that the solar system's 4.5 billion years old? Well, that's the most certain evidence we have of how old it is. That doesn't mean that it's not way older. It just means that's the only thing we can certainly say about how old it is. And that gets kind of concretized in people's minds into, like, almost all scientists today will tell you the solar system is 4.5 billion years old. And that's how it's taught. And it's interesting how we convert theories and understandings into facts. I think this is, like, in some sense, a real disservice and leads to a lot of the scientism and people's dogmatic religious belief in their own theories, because oftentimes as scientists, we don't have a lot of time in our education to go back and actually examine all of the possible ideas that other people had. And honestly, I wish we had more time. If this, it'd be great to have an upper level seminar where we could look at just one aspect of the solar system and trace the history of the ideas about it, because they're so wide ranging. And these people were very, very intelligent. They were very rich and had a lot of time to sit around and think about these ideas and write books upon books about them. And some of them are well elaborated, and there's certainly some really good ideas that have just gotten, glossed over as the years have gone on. And if you really start talking to scientists that are moving mountains today, they all have a really good grasp of the deep history of science, right? And it's kind of a bummer, because we don't have a space for that in our modern university structure usually, right? You're going to all sit through, this is many of you, this is probably the extent of a science course that you're going to have, and we can only do so much in an hour and a half lecture each time with each one of these topics. I mean, we're talking about the entire solar system, so it's very difficult with any detail to get into those. But that would be a freaking amazing course if we had time for an upper level seminar about that. Any more questions before I move on from the birth of the solar system to talking about the Earth? All right. Let's So there it is, our Earth. It's a medium-sized planet. It's about 12,760 kilometers across. And it's composed primarily of really heavy stuff like iron and silicon, oxygen. And, you know, this is weighed in, just to touch on what we just talked about, this is weighed heavily into the idea that since it's towards the interior, it formed there because the heavy stuff would be closer to the center. And that's not totally clear why the really heavy stuff like Earth is made out of didn't end up inside of the sun. This is an interesting point to think about. But here it is. It's the only place that can support liquid water on its surface, and this is probably why it's the only place we're seeing life at right now. You know, there's some discussion of maybe there is subsurface water on some of the bodies that we're starting to visit, and it may well be possible that there's some sort of life down there. It also may be possible that we don't understand what life is, and life can take on lots of different configurations depending on its environment. But as far as we can tell, water, liquid water in particular, is absolutely fundamental to life. And so we're in this really nice little Goldilocks region where it never gets too hot, never gets too cold. And this is what's fundamentally unique about our planet. What's cool, though, is like we're starting to look out into the beyond our own solar system, and we see a fair amount of these planets actually that have these characteristics. You know, a lot of them are quite large, so gravity might be an issue if you get too big. You know, they might have the right composition and atmosphere. They might even have liquid water, but they're extremely large, like on the order of Jupiter or something, approaching that order. It also may be that our method for looking out into the exoplanet world only allows us to see things that are quite large. So there might be plenty of Earth-sized planets that we're just missing because they're too small. Remember, when you're looking for exoplanets, all you're looking for is like a shadow that's passing in front of the star. And so you're naturally only going to see something that's quite big. So hopefully there are more, because we're going to need a new house eventually. Some properties. This is one of the figures from your textbook. I think that it's worth mentioning. I mean, one thing that's really interesting here is that a lot of our standardizations are based on our own planet, right? The atmosphere has 1 bar pressure, right? Well, of course, bars are defined by how much pressure we have on Earth. And it's not clear how that pressure has changed over the years, too, which is a real nightmare for looking into deep geology. You know, you can look very carefully at the composition of the atmosphere in the past. You can't easily make any statement about how much of that atmosphere was there in the past, which is a really important point, and we'll talk about that in a minute. Of course, the astronomical unit is defined by our distance to the sun. The year is defined by our orbital period. And so we, again, have this very Earth-centric way of looking at all of the planets. So let's talk a little bit about how the Earth is set up. You know, our only real direct experience in terms of being able to look at something, touch something, analyze it directly comes from the crust, which is wild because, you know, we know more about the surface of Mars and the moon than we do about what's truly happening 5 kilometers below our feet right now. Because all we can do is infer from indirect means what's going on. You know, we can get a little bit of magma, which, you know, we have different reasons to believe comes from different depths. But when you start talking about what's happening, you know, hundreds of kilometers below our feet, it gets a little bit more murky. And so a lot of the things that we use to infer that come from looking at how, you know, how sound passes through the Earth. We can learn about the material structure of it that way. We can learn about it because we have to explain why we have this huge magnetic field. And it turns out that in order to have a huge magnetic field, you have to have very particular kinds of motion deep within the Earth in order to explain that. And I want to definitely go into how that magnetic field's generated. It's a really cool story. So these are these indirect shadow means of measuring the interior, how we've come up with this model that we have today. And I'll get more into it. We're going to go through each one of the layers in detail. But it makes sense. Well, I want to tell a little, let's tell one little story. So if we want to look deep inside of it, one of the ways that we can do this is we can look at how earthquakes propagate, right? So what's an earthquake? It's just essentially a vibration on the outside, at some depth, relatively close to the surface, and it sends out waves of compression throughout the Earth. And so this very brilliant woman, he was a Danish geophysicist. Her name is Inge Lehmann. She started analyzing seismic data and noticed that you could actually measure the reflections, you could correlate the different earthquakes and the time at which they arrived on different sides of the planet. And by looking at this, she was able to see that different waves were being actually reflected off of different surfaces and traveling through these different layers, and made this model that we essentially have today, where you have different layers of solidity that are discrete. There's actually transitional zones between each one of these borders. It's not just like a complete gradient. There's actually discrete layers as we go downward. And so this idea of seismic shadows became integral into our model of the Earth, and we still use it today. So let's talk about what we can actually see at the crust and the story of our crust. So most of the crust is oceanic crust by a small majority, which means it's stuck underneath the water. And that type of crust is called basalt, which is essentially volcanic rocks. You know, the seafloor is actually extremely young, which is an interesting puzzle, and it's going to feed into how we interpret everything, which we'll get to in a moment. You know, the oldest parts of the seafloor are only 200 million years old. This is very interesting. So, you know, the crust is constantly remodeling itself, and this gets into why it's so tricky to actually date this whole rock altogether. The continents themselves are a little bit different. They're thought to be comprised of a different kind of rock, which we call granite. And these rocks are made out of silicon and oxygen. It's different. It's also volcanic in nature, but these are much stiffer and they're much older. So continental crust is about 20 to 70 kilometers thick. It's actually relatively thin, and it's thicker over these mountain regions. And we'll talk about our theories for how mountains are built. So the crust is these different types of basalts can be loosely grouped into a few categories. The rock that immediately cools from a molten state is called igneous. There's also this rock which is called sedimentary, which comes from recycled pieces of igneous rock that layer up. And this is like your sandstones, shales, and limestones. There's another type of rock which is kind of interesting called, well, this is another picture of sedimentary rocks. There's another type of rock called metamorphic rock, which is quite interesting, which is like some sort of igneous rock that's been folded and reshaped by processes. And this is really fascinating because if you go out and start looking at the landscape, you notice that the Earth has been sort of tumbled, and the crust has been tumbled and shaped and folded in all these really interesting ways. And these observations are what led to the great tectonic debates of the 20th century in terms of how this happened. Today, we think about these plates. Well, today, most scientists think about these plates as crunching into each other. And as they crunch, there's one plate that's being pushed under the other, and this leads to a lot of the folding that we see in the record. And there's alternatives that were entertained. We'll play with those in a minute. Then finally, there's another type of rock, the last type of rock, which is called primitive. And what's interesting is we have almost no primitive rock on Earth except for meteors, because the canon goes, if we follow the nebular hypothesis, that these meteors, meteorites, I guess, because we found them on Earth, the meteors formed at the same time as the planet and all of the planets under this steady state idea that the planets form in place. And so if we want to know something about the oldest parts of the Earth, we look at meteorites. And this is obviously a hugely indirect leap of faith, but it seems like meteorites compositionally make sense with the density models that were worked out using the seismic waves. And so there's reason to believe that meteorites are actually quite similar to the interior of the Earth. Now, whether that's because they formed at the same time in the same regions as the Earth, or whether it's because they're leftover chunks from some ancient dead planet, it's really up for debate. Although your textbook doesn't entertain the latter idea. So the biggest chunk is called the mantle. And the mantle, we have to talk a bit about the mantle because the mantle plays an important role in the process by which this tectonic business unfolds. It's sort of the engine which is thought to move the crust about. Now the mantle is strange because it is in some sense liquid, but it's a very viscous liquid. It doesn't flow very easily, and actually it flows better at the top than at the bottom because there's some separation of density. You know, you can think about it like honey versus like water, you know, or something like, maybe that's not a good example. Different weights of motor oil, which flow better depending on their weight, depending on their density. Okay, so this is the model that we have that everyone has probably seen before. So we start off with some sort of supercontinent, and you know there's different ideas about how this may have happened more than once, but generally speaking, people are interpreting the rock record in terms of this giant supercontinent which has been drifting apart. Now you notice what's really interesting, you probably can't see the time scale here. This is actually only happening over a few hundreds of millions of years, which is a very small portion of the planet. Now, why is that? Well, like I said, the ocean floor is only 200 million years old, so they need to make all of this happen very quickly in this model. So these plates are cruising apart from one another. And it does seem that they have moved apart from one another. So whatever theory was being argued when this was being developed had to make sense of this piece of data. If you look at the location of different fossils, you know, from plants to different dinosaurish reptiles, what you find is that the bands of fossils are continuous across the different continents like this. And of course, the continents fit together really nicely like puzzle pieces. And this was what really kicked the ball off because, you know, prior to the concept of tectonics, that is that the plates themselves are moving, prior to this, people were trying to explain this data. This is very early data in the 1800s. People were trying to explain this by saying, okay, well, there was some sort of land bridges that would appear and allow the animals to travel between these regions, but they just couldn't find evidence of that. And so the first person to really patch all of these ideas together was this gentleman named Wegener. He was a German geologist. And Wegener's idea was essentially what we call plate tectonics today. He called it continental drift. It was the idea that there was this supercontinent that moved apart over the ages. And you know, Wegener was treated as something of a crank in his lifetime. Everybody thought this was a super fringe science idea, and nobody liked it. He actually did not live to see it accepted, which is quite tragic. And I wonder how often that happens, actually. You know, there's probably some lunatic out there right now explaining something very fundamental that none of us will ever appreciate as long as that person lives. So the question became, and oh, this is really worth mentioning. So why didn't people like Wegener's ideas? Because they couldn't come up with a mechanism for how the plates would be moving. They're like, okay, man, it looks like the plates may be moved, but how did that happen? And he couldn't explain it. You know, he tried on some some pretty loony ideas, unfortunately, with explaining that, and nobody bought it. So a little bit later, people actually started to come up with mechanisms for how that could happen. And the mechanisms, I wish I had a picture of this right now. But the mechanism actually had to do with these conveyor belts within the mantle that were actually due to convection. Does anybody know what convection is? Can you explain it? Yeah, exactly. Do you remember why why does the heat cause things to rise? Right, exactly. Yeah, so it's a density-based uh, imagining of this motion. So if there's these convection conveyor belts, then okay, they can maybe, the plates can surf on top of them. And so this was fantastic. I don't have the name of the person who proposed this written before me. But people went out and they started looking at the different openings in the earth, right? And they found these trenches. They found these rifts in the ocean. And they found eventually what we know as subduction zones, right? Where the crust actually seemed to be sinking down beneath another. One plate seemed to be sinking beneath another. And this jived really well with this convection idea because you have all these different motions going on. And so this is essentially the idea that we have today, that most scientists have today. I mean, there's some interesting issues with that. You can identify these places where there are, in fact, rifts, and they do actually seem to correspond nicely in some cases to where this new rock is appearing, right, as we see in these oceanic trenches. But what's very strange is that there's other rifts, right? There's a huge one going through Africa. There's several other rifts. I wish I had a picture of this. That you don't see this kind of activity at, which is very strange. And actually, when we look down, I could have done a better job of ordering these. I'll come back to it. Yeah. So when we look down, and we actually look at where the magma is seeping up from the surface, this is what we see. This is calculated with a kind of these images are made with a kind of echo, similar to the seismic echoes that we were doing. And what we see is that there's actually a great deal of upwelling of magma, which these are magma plumes, they're called, right? But they're not really correlated in any way to the rift zones, which is very strange. And so no one's been able to actually see these convection currents. That's where we're at today, right? The convection mechanism is totally a great idea, but we can't find those convection currents, right? And so, you know, the way I'm looking at this theory, it's very much still open for debate as to what's actually happening. We'll talk about volcanoes at the end. And again, here's one of those mantle plumes coming up. Now, it is conceivable, and people have tried to reconcile this by saying that, okay, these convection currents are actually happening as little eddies right at the very surface, which may be the case. But it brings us back to this debate. And here, by the way, these are all of the different hotspots. This is where the upwellings are actually occurring. And what's very strange is they don't seem to correspond at all to the rift zones, right? Because if these plates are surfing along, you would expect that at each margin you would have tons of these hotspots. But it's not totally what's happening. So these are the two gentlemen that were having it out in the 1950s. So we have Wegener there on the left. He looks a little bit happier. And then we have Carey on the right. So Wegener is the one who's come up with the tectonic model that we have today. Now, Carey's model was a little bit different. Carey thought that he was very concerned about the sea floor spreading being incompatible with these with the motion of these plates. And he proposed this other idea, which was essentially shown here on the right, which is that, hey, the Earth just used to be a lot smaller. Everything, all of the fossils make sense because the continents were, in fact, in a Pangea formation, except they just blanketed the entire Earth. You know, and this was very seriously entertained in the 50s. And again, the problem was Kerry had no mechanism for how this would happen. You know, it takes a great deal of energy to squash a planet down, right? And he wasn't sure how this would happen. He didn't have an idea about it. You know, somebody calculated that if you wanted to chemically expand the Earth like this, right? You know, and today, by the way, expansion Earth people are kind of treated like flat earthers, right? But this was a very seriously entertained idea less than 100 years ago. You know, people argued that if you wanted to expand the Earth, you would need to take something like all of the chemicals on Earth and combust them, and you still wouldn't have enough energy to blow the thing up. So this idea was thrown out, and we're left with this tectonic idea that we have today, which is also, like I said, troubled by the absence of, it has a conceivable mechanism, but we're not able to actually find direct evidence of that. And so there have been some really cool additions to that theory. One that I mentioned that Marvin Herndon championed about the birth of the planets, which is, you know, if the Earth, let's say, in the deep past, started off as a very gassy planet, right? Like with a really thick atmosphere, something like as thick as Jupiter's atmosphere, so it's almost liquid-like. Well, if you pull that off, then you only need maybe 2,000 kilometers of atmosphere piled on top of the Earth in order to squish it down. Because, you know, you can calculate this very easily. The Earth is just like all materials. It has a squishiness to it. We've talked about this a bit. It has essentially a springiness. This is Hooke's idea that all materials can be characterized by this spring constant. And so the spring constant tells you basically how much pressure you need to put on something in order to deform it. And it turns out to be not a crazy amount of pressure necessary to pull that off. So Marvin's idea and a number of other people have advocated that perhaps there was a thicker atmosphere. And you know, I find this a really fascinating idea. It's by no means an accepted idea, but I actually had the pleasure of speaking with an astronaut named Don Petit, who actually did his PhD at the University of Oregon. And when he was doing his PhD, his thesis revolved around this idea of how can we explain flying dinosaurs? Because you see these pictures, they're actually not technically dinosaurs, but they're called like Quetzalcoatluses, and they're adjacent to dinosaurs, you know, sort of like chickens. But they were alive at the time of the dinosaurs. They have very little wings for how big their bodies are. And in fact, if you plot the body mass with the flight characteristics of all flying things, they sort of fit on a line, but these dinosaur birds don't really match the trend at all. And it's been a real challenge for people to explain how these dinosaurs flew. And of course, one possibility is they didn't fly. They were sort of like flying squirrels, right? They just climbed up on something tall and jumped off. Or like turkeys do this a little bit. So that's one possibility. But Dr. Petit, he and his advisor had this idea that, hey, actually, if the atmosphere was only something like 3 times thicker 65 million years ago, then these animals could fly just like normal birds, essentially, because you're actually adding buoyancy to the environment because you have a much denser atmosphere. So there's a little bit of an interesting story there. And like I said, it's impossible to actually directly measure the pressure of the atmosphere 200 million years ago. We can say the composition was essentially the same as it is today, but we can't say how thick it was. And so it's a really cool idea just to play with in your head a bit. There's certainly some issues with it. There's an angular momentum issue. You know, angular momentum comes into every one of these discussions. And of course, the problem is if the Earth, just like the figure skater, if the Earth changes in its diameter, then it has to slow down. And it doesn't seem to have slowed down. But we have the moon, right, which is something like a long arm of the system. And so depending on how you model the dynamics of the moon and how it was behaving in this time period, you may be able to rescue that problem. What's up? Well, so the composition would have, that's a great question. So the composition is hypothesized to have been exactly the same. The partial pressures would have all been the same. Same ratio of all, each breath is going to have the same ratio of, nitrogen and oxygen, and so on and so forth. It's just that there's more of it. Yeah. Dinosaurs are very strange too. They're freaking enormous. Like it's difficult. Other people, there's a gentleman who's a physics professor in, I think, somewhere in Colorado. I don't want to say which one of the schools. Named David Esker, who has tried to make arguments that the gravitational pressure of the dinosaurs, like especially the big ones, like the brontosauri, like they would have been so heavy they would have crushed their own legs, basically. And people have gotten around this. They say, okay, well, the brontosauri, I don't know how you say it. The brontosauri lived in water exclusively, so they're floating. And it's like, okay, maybe, But these are all just stories that we have to tell to explain what we see. And it's not totally clear what's happening. So anyways, I just want to expose you guys to this interesting idea. I put a little movie in it in the Moodle if you want to learn more about it that my wife and I just made, where we bring in some different people's perspectives, and we talk about the criticisms of it as well. So, okay, let's talk about the core a bit, because as usual, I'm taking too long to talk about everything. So beginning at a depth of about 3,000 kilometers, we see this core, which has a diameter of about 7,000 kilometers. The outer core is thought to be liquid, which is a very critical region for the magnetic field that we're going to talk about in a second. And then there's some different density-separated layers. And what's really, really amazing and absolutely critical about our core is that it has this magnetic activity, right? And the magnetic activity is able to shield us from all of the terrible things that would absolutely eradicate us from the face of the Earth. And again, Venus is a great example because Venus is very similar to Earth in composition, but it doesn't have a magnetic field. And it's kind of a disaster on Venus. You wouldn't want to be there. So there's no doubt that the magnetic field, which we call our geomagnetic field, is important. This, I think, is a model of about 6,000 years of geomagnetic activity, where you can see that the polarization of the magnetic field is in red and blue alternatively. And every few hundreds of thousands of years, we actually go through a pole reversal. And we can talk a little bit about what that even means in a second. But I don't think that it's fair without actually trying to understand how this happens. So if I only accomplish one more thing today, I want to talk about how it works, okay? And I don't think that it's possible to talk about how it works without understanding how magnets, especially, let's not talk about bar magnets today. They're a special case. Let's talk about electromagnets, because this is an electromagnet, actually. Okay. So I think that what you normally hear in your textbooks is that the best way to understand magnets is that atoms themselves act like little magnets. And this is good and a good and bad way of looking at it. So it requires us to conceptualize of this idea of spin, right? Electron spin. You've probably encountered it in your basic chemistry classes. The orbitals have spin-paired electrons and so forth. It's this nebulous abstract concept, but I think that we can actually make sense of it. And I've actually spent a great deal of time trying to visualize how this looks. Now, the spin of an electron, which is of course the outside shell, the electron is the outside surface of the atom. It has a particular kind of symmetry to it, which is called SU2 symmetry. You don't need to remember that. But what it essentially means is that the surface is going around twice before it gets back to its starting position. And there's a lot of, this has essentially caused people over the last 70 years to say, well, it's just some property we can't understand, because what on earth would go around twice before coming back to its starting position? And I don't think that's fair. I think that there is a way of visualizing it, and I've made this animation here to show you that in this case, if you imagine the surface of the atom, let's play it again. If you imagine the surface of the atom rotating, but you also imagine it involuting on itself, that is, feeding into itself, then you can see, and I've marked the outside with a pink stripe so you can see, that the involution could perhaps happen twice per rotation cycle. And I'm not saying this is how it works. I'm saying this is one idea of visualizing how it might work. There's something about the surface of the atom that has a particular rotatory fashion. So the long and short of this is that if you have an atom, which is roughly spherical, and it has a spin axis, which was shown up there earlier, we can call this the spin. It has a very particular rotatory motion as well. Now, if the atom is just tumbling in space all by itself, it might make sense to treat the pole of the atom as the pole of a magnet if the atom is to be treated as a magnet. This makes a lot of sense. But something really interesting happens when you get groups of atoms together. When you have groups of atoms or groups of orbitals that are all in contact with one another, so if we put them all in contact with one another, we get something, and we have them spinning in this particular fashion, right, like this. Then they're able to produce what is called a current. This is a vector. So this is essentially what we mean by electricity, is that when these atoms are in contact with one another, they're able to actually perpetuate that momentum in a direction. It's often taught in your intro textbooks that electricity is the flow of these little electron bead things. But this doesn't work out because the speed at which this impulse is able to transmit to the other end of the wire is much faster than those actual surfaces can travel due to essentially how much inertia they have. And so there's some sort of propagation of this motion along this lines. And so we call this motion, which is being propagated, we call this electric current. And then we say that the lateral motion that's associated with it over here is called the magnetic motion. We give it this little symbol. And so what happens is you can actually, and actually, if you take two wires, this is a hypothetical single atom wire. It's a little bit silly. You wouldn't actually have one of these, except maybe in space, like some ions could do this. But what happens if you take a bunch of these and you take these wires and you make little coils out of them like this, then what happens, and here's all your atoms lined up here, right? What happens is that their individual lateral motion rotates inward like this. Let's see if we can see this. And what you can start to see is that on each loop of the coil, the outer motion of the electron shells actually starts to align so that they're all actually doing the same thing, such that the whole coil is rotating into itself, right? And real metals, this single atom wire is a nice way of thinking about it, but real metals are quite complex. They have multiple orbitals, but they still have this synchronicity to them such that they can have a cohesive surface motion. And we call this thing a solenoid. And this is extremely useful technology in everything from electromagnets to radio wave generation. One thing you can do to reinforce the magnet is put something very magnetizable at the center of it. If you want to build a really strong electromagnet, you put something at the center. I actually want to show you. I just made one of these. They're not quite difficult to do. Let me see if I can switch this over. So all I've done here is I've taken a wire, and it has a thin piece, like a little painted coat of insulation on the wire so that it doesn't transmit electricity between the different loops. And you wind it around I made this out of a pen and a little piece of, a little stick here. And you wind it around here, and what you do is you've produced one of these magnets over here, which has a south pole and a north pole, ultimately. Now, this is essentially an electric motor as they're made today. And the basic way that it works is that when the current crosses this wire, there's a little piece of wire running down the sides here. You can see it like that. And there's another one on the other side here. And what happens is that when contact is made between the two, they're touching these nails here. When the contact is made, it creates a magnet inside of this coil system. And I don't know if I hope you can see, I've written north-south here. The fixed magnets are oriented opposite the coil which generates, which appears. And it appears, let me see if I connect this to a battery, hopefully it'll just work. I'll have to kind of kick it over. Okay, there it goes. So what's happening is that every rotation, the magnet is appearing, and then when the contact is broken, the magnet disappears. And it's just appearing for just the right moment that it can push off against the south side, right? Because you can imagine in our coil system, if we had this same motion of all of these atomic shells moving inward and upward, if we turned it against itself, they would be pushing against it. And that's what drives the electric motor. It's a really simple idea, and it turns out that it's actually what's happening inside of our core as well. So let's take a look at that. Now, well, actually, before we do that, you might ask yourself, okay, well, so the atoms are, pushing against one another and so forth. But you're like, hey, how is it, the magnetic field is reaching, hundreds, thousands of kilometers into space. Some portion of it, especially on the downwind side, is reaching maybe out as far as the moon. How is that possible? How can these atoms reach so far? And I like to point out that this is a particular rendition of the quantum wave function for an electron, particularly for the different s shells of an atom. And what's fascinating about the atom is that most of the electron is found quite close to the nucleus. This is the center where the nucleus is. And the surface seems to dissipate at a distance. But what's really fascinating is that it never dissipates completely. The atom never runs out of stuff for some reason. It literally can reach, at least according to the models, the best mathematical models we have, the atom can reach indefinitely. It can certainly reach as far as its neighbor. And if you imagine that the whole of the Earth and the whole of outer space is really a network of atoms that are very distantly in touch with one another, then it becomes possible to understand how these magnetic motions deep within the Earth can be relayed across the various atoms at great distances. So nothing spooky to it. It's not magic. But we don't totally have a great model for how this works in terms of materials yet. So this is what you see inside of the Earth. It's basically the same thing. You have an interesting phenomena where, forget about the inner core for a second, but you have this outer core where there's liquid metal. And because the Earth is rotating, and because there's convection, you get these little eddies forming in that liquid metal. There's also this organizing principle called the Coriolis force, which is responsible for why hurricanes have this spin. It's very similar to what we talked about with the pendulum, for why the pendulum rotates, because there's not just this forward back and forth momentum, but there's also this rotating fashion to it as well. What this results in is these standing eddies. And so what it's thought is that these eddies are each acting like little coils, little magnet systems. And in effect, they all sum together to a cohesive magnetic signal, which is able to affect all of the atoms in the atmosphere, all of the thinned ions that collect at the edge of the magnetosphere. And there you have it, a magnetic field. So it's very important that, getting back, maybe we'll close by talking about why we have a magnetic field and Venus doesn't. And this is a tricky one to explain. I'm not sure we have the full story yet, but our crust has these cracks in it. And when you told us about how convection works, you mentioned that there needs to be a gradient. The heat needs to be able to escape the system, actually, right? And if you have a closed lid, like a perfectly closed lid on a system, it's not clear that convection is possible in that case. So the standard explanation you'll hear is that the Earth has a magnetic field because we have these cracks in our crust. I mean, there's no doubt that the cracks in our crust are unique and quite amazing, and we don't see them on other bodies out in the solar system, which is very strange. Perhaps Jupiter has a nice magnetic field actually, but it's not clear that it has a lid necessarily, right? It's mostly this liquid gaseous ball, and it probably does have a core. Again, why do we have what's the point of the deep solid core in each one of these objects? The point is that when you have something magnetizable like iron, right? You guys have probably magnetized like a paperclip before or something, right? Iron has this ability to rearrange its shells in commensurate form with the field that's applied to them. And so the cool thing about having a solid inner core is that it stabilizes the whole system. It entrains that iron, that nickel, to hold the field in shape, because if it wasn't being held in place, maybe you'd have magnetic field reversals every 5 minutes or something, right? It'd be very unstable. And so our inner core is the ballast. Let's stop there. If anybody has questions, come talk to me afterwards. And yeah, thank you guys.